Transfer and Metering Conference, dedicated, of course, to the latest innovations in metering technology. So thank you so much to all of you for joining us here this morning. Well, we have brought together some of the leading voices in petroleum, regulation, technology and innovation, who are all here to give us an insight into the latest techniques, project strategies, budget planning, timelines and technical hurdles that are shaping the future of the industry. And yes, we're very excited to welcome you all here for the next 2 days for knowledge share, best practices, business opportunities, of course, and fostering those all-important connections. First and foremost, though, of course, we have to say a huge thank you to all of our partners and sponsors who have made the event happen. So a huge thank you to OGS, Citadel Engineering Company, Kelton, Solve Flow Measurement, BMX, Wicker and EIC, the Energy Industries Council. So please do join me in a round of applause. Thank you. Right, just a little bit of housekeeping and some housekeeping rules to be aware of if possible. Please do switch your mobile phones to silent. It can be a little bit distracting when a phone goes off up here. We'll have our coffee and networking break a little later on, and refreshments are always served just at the end of the exhibition hall there as well. And of course, in that break, we very much encourage you to make sure to visit our exhibition space, as we are here, of course, to be a unique networking platform, and we have a lot of exhibitors very eager to meet you today here as well. Now, we're also delighted to invite you all to our networking dinner this evening. That'll be held at Chillo's from 6 p.m. tonight. Now, we would also love to make the event as interactive as possible. So after each of our sessions, we have a good 15 minutes to get some Q&A out of all of you. So please do not be shy, don't hold back, and we'll get some really good conversations going with those questions that hopefully you will be asking a little later on. For any further information, please do refer to the QR code. I'm hoping that's up here, yes? So please do refer to the QR code for the agenda and any more information that you might need. And if you'd like to share anything that you've heard here today, you can use our handle, which is CTMC 2024. Now, just very quickly, just to let you know that our second speaker, Hussein Al-Abdin from Kuwait Oil Company, will now be doing his session just in the meeting room just opposite here. So you can head on over there, and we're going to break for coffee at the same time. However, we can only have about 12 people in that meeting room, so please do attend that if you would like to as well. Well, ladies and gentlemen, we start the day with our opening keynote, and sadly, the CTMC 2024 event organizer and founder, Shahrir Majliseen, who is also the CEO of Citadel Engineering Company, could not sadly be with us here today, but he has sent in this video message.
Dear esteemed guests, distinguished speakers, sponsors, and participants, while I regret that I cannot be with you in person for CTMC 2024, I am truly honored by the strength and commitment of this year's gathering. Custody transfer lies at the heart of the energy sector, ensuring precise, trusted transactions that impact economies, industries, and communities worldwide. It's essential for the Middle East, a key player in global energy landscape, to be on everyone's radar as the region continues to set the pace in both traditional energy and new energy solutions. The Middle East's strategic role in global energy, especially in the advancement of hydrogen measurement, makes this a critical time for OEMs and regulators authorities to deepen their collaborations. The rise of hydrogen as a sustainable energy source means that accurate measurement is paramount to ensure efficiency, safety, and scalability. Here at CTMC, we are committed to fostering these connections as OEMs and authorities play an essential role in setting the new standards and advancing technologies that support both traditional and emerging energy demands. I extend a special thanks to OGS, who has been with us from the beginning as a valued partner and a strong supporter of the CTMC committees. Their dedication has been vital in shaping this event's success and our shared mission of advancing measurement accuracy and efficiency in custody transfer. To all exhibitors, speakers, and sponsors, I wish you a successful and rewarding conference. May you leave CTMC 2024 with fresh insight, strength, connections, and actionable knowledge that will enhance your contributions to this vital field. I hope to meet each of you in person at the next CTMC in Dammam, Saudi Arabia, as we continue to shape the future of custody transfer and measurement together. Warm regards. Thank you.
The CTMC organiser and founder there, who, as I mentioned, could sadly not be with us here today, but emphasising that we, strengthen our connections and really develop actionable knowledge. So we really hope we can take something away from the next 2 days. Well, providing traceable metrology for the energy transition is essential for oil and gas professionals adapting to a lower carbon future. And our first session of the day is going to take a look at advanced measurement techniques and standardized metrics for sustainable practices to align with net zero goals. So please do join me in welcoming our first guest, who has significantly contributed to the development of several ISO standards for correlates and ultrasonic flow metering. I beg your pardon. As the Deputy Chair of the British Standards Institution Committee, CPI 35, Velocity and Mass Methods, he brings extensive knowledge and leadership to the field. He's also written numerous conference papers, contributed to various R&D projects, and even holds a patent for a flow meter verification technique. He also chairs the 2024 Global Flow Measurement Workshop Committee, where he focuses on helping industries meet the challenges of fluid flow measurement during the energy transition. So, ladies and gentlemen, please do join me in welcoming Colin Lightbody, Principal Consultant at TUV SUD National Engineering Laboratory. A very warm welcome.
Good morning, everyone. Thank you. First of all, I just want to say thank you to Citadel and CTMC and Sharir and Laura for the introduction. Obviously, it's a shame that Sharir can't join us today. But it is an honour and a privilege to be standing here to give the opening technical presentation of the CTMC 2024 conference. So just as Laura alluded to earlier, my presentation today is providing traceable metrology for the energy transition. So I'll talk a little bit about my employer, TÜV SÜD National Engineering Laboratory. I'll talk a little bit about proving and challenging fluids. And then I'll talk a little bit about our existing calibration facilities, and that's to try and emphasise the depth of experience that my organisation, not my organisation, that the organisation I work for has when it comes to metrology and the fluid properties of complex fluids. Then I'm going to talk, about hydrogen and CCUS, which is bigger. It's amazing the number of CCUS and hydrogen projects that there are here in this part of the world, Central Asia, and the complexities are equal to those of oil and gas. They have to be addressed, and what I want to do is explain how my organisation is part of that solution-seeking force that's pushing forward metrology for new energy fluids. So, one corporate slide, because if I don't put it in, I'll get sacked. TÜV are a global testing, inspection and certification company. We've been doing it for more than 150 years. We have more than 1,000 offices, including many in this region of the world. We have more than 25,000 employees, so we are a sizable company. And as I say, testing, inspection and certification is the game. However, that's not why we're here today, so I'm just going to get into the substance of my presentation. We're a very small part of TÜV. I think there's about maybe just under 100 people work for the National Engineering Laboratory. And primarily we're known for flow testing and calibration, flow consultancy, and flow measurement R&D. And I really can't overemphasize the impact that we've had on the development of oil and gas metrology over the last 40, 50 years. And we'll talk more about that. That's the substance of this presentation. However, there are other things that we do. And I very quickly just want to make you aware that my colleagues who do computational fluid dynamics and data analytics and data science impress me on a weekly basis. I am blown away with what our CFD guys can do and what information our data scientists can get from large data sets. Just a couple of examples. We've recently developed and released a technology called Flare Sure, which is really, quite vital for all operators now, especially in this world area. Everyone signed up for OGMP 2.0 to get rid of methane or to minimize methane emissions. So we've developed a real-time flare optimization tool, which hopefully turns a very inefficient flare to a very efficient flare using computational fluid dynamics and software. We can see there that we allow operators now to manage their flares in real time and hopefully be able to generate combustion and destruction and removal efficiencies well in excess of the 98% which is currently required by industry around the world. And also, having a data science team and having a multi-phase flow laboratory puts us in a very unique position. It's allowed us to develop and test a virtual flow metering solution, which has now been made available and is operating successfully in a couple of platforms back in my region of the world, generating flow rate readings to within 5 or 6% of the reference readings without a flow meter. Really quite impressive. Anyway, calibrating flow meters. A couple of things I want to talk about: in situ proving and challenging fluids. The advantages of in situ proving are well documented, well established. And that's the end of my presentation, folks. Thank you very much. I'm not sure why. Sorry, folks, my little forwarding things, I think the battery's gone flat, perhaps. Unlike Donald Trump, I'm not going to start dancing for 40 minutes. Nope. Well, how much? Yeah, there we go. So, everyone knows that using a prover, not everyone knows, most people know that using a prover is the best thing to do for validating the performance of a meter. The lowest uncertainties, and you eliminate all the concerns over installation effects or fluid properties because you're using your skid and your fluid. However, Not cheap. The purchase cost of a prover is high. The cost of ownership is high. Maintenance, water draw, spheres, switches. You can rent one, but again, the cost of rental is quite high. So, very often, so not every metering point can justify its own prover. I'm sure the prover manufacturers wish that was the case, but it's not. So very often, flow calibration at an accredited facility is the best option. But it's clear it's not always straightforward, and it's a couple of these things that I want to speak about today. Especially challenging when the fluid is challenging. Now, what do I mean by a challenging fluid? Maybe something like high viscosity. There are quite a few fields in this world area that have very, very high viscosity oils. In fact, most of the world's reserves of light crude oil are being extracted, and, relatively speaking, there's more and more heavy oil left, viscous oil. High pressure and temperature brings its own challenges. 2 or 3 phase fluids, that's how it comes out the ground. We want to measure it when it comes out the ground, and it's not easy at all. And of course, we're moving now to new energy sources. Carbon dioxide and hydrogen now. I know that carbon dioxide isn't an energy source, but you all know what I mean. It's a byproduct that we want to get rid of. So we're going to try and measure this. Well, we're based in central Scotland. We were called NEL. Everyone calls us NEL, the National Engineering Laboratory. We're now part of TÜV, as I mentioned. And that there is our facilities in East Kilbride, a kind of modern town outside of Glasgow. And we have 15 test, research and calibration facilities, either fully operational or under construction, and I'm hoping to speak about these today. We love challenging fluids. We've made our name on metrology for challenging fluids. And we do have an awful lot of experience. I didn't make that picture black and white. That was a black and white picture that appeared in the Glasgow Times, I think at some point in the 1980s. So we have an awful lot of experience when it comes to fluid flow metrology and understanding fluid properties. So I'm going to talk about 3 of our facilities here, just to highlight a couple of things which I hope will be of interest to people in the audience. We have a facility called the EPAT, the Elevated Pressure and Temperature Facility. It's a liquid flow loop. Its primary reference is a small volume prover. The secondary reference meters are turbines and ultrasonics, for what it's worth. And it has a very low uncertainty of plus or minus 0.08% at a 95% confidence level. The key here, the point I want to get across, is the pressure range. 4 to 100 bar. Doesn't cover every industrial pressure, but it does a significant proportion. And 20 to 80 degrees C, again, doesn't cover every scenario, but it takes in a large amount of the conditions that our customers see. And also, we can control these pressures and temperatures to less than a degree C, and I think it's about 1/10 of a bar or 0.2 bar. And it's that control here that's the key to the success and the value of this facility. Here I have a mass flow meter. It's a Coriolis meter. If there's Coriolis meter manufacturers here, they know all this. I'm not here to decry their product. Fantastic meter. So I've calibrated that meter at 5 bar, and it looks spot on. 0.1% maximum deviation from the reference. Everybody's happy. Low pressure calibration in line with the manufacturer's specification and industry expectations. What if I change the pressure? I'm now calibrating it at 5 bar, 20 bar, 40 bar and 80 bar. The performance of the meter shifts dramatically. The 80 bar calibration, which is not an unrealistically high pressure for, say, the offshore industry, the meter's now shifted almost 0.7%. That's way outside the expectations. Now, I know that nowadays Coriolis meter manufacturers have pressure corrections, but if you're using this for something like custody transfer or allocation, it has to be traceable. So the key advantage of a facility like this is that the details matter. It's not enough to just stick it in a water line calibrated at 5 bar. Details matter. If you want that low uncertainty and you want traceability, you have to be very thoughtful about how you're going to calibrate your meter. Next, I'll go on to their oil facility. Our oil facility is the primary standard. It's the UK's primary standard for liquid flow measurement. It is a liquid flow loop. It's a gravimetric primary. It's a weigh tank. PD meters, which are just about as old as me, for the and that's old for the secondary reference meters, but we love them because they're repeatable and they're reliable. I think people are surprised sometimes when they come to our lab and they expect to see a 1,000,000 path ultrasonic or a 50 tubed Coriolis meter. We use PD meters because they're repeatable and they're reliable. We don't care how accurate they are because we calibrate them against our gravimetric tanks. The repeatability is key for us. The measurement uncertainty is very, very low, 0.03%, way more accurate than most customers need. The key here for me is the wide range of viscosities. I got this figure last week. It's currently, we can do about 600 centipoise or 800 centistoke. Used to be 2,000 centipoise, but we've stopped doing that because it was just too much. And why is that important? Why is that important? Well, here, again, I'll use an example. We have a Coriolis meter, and we've calibrated it in kerosene at 2 centistoke. Yep, everything's fine. It's within the industry expectations, and it's within the manufacturer's specification. What happens if I increase the viscosity? So everything's fine, or a low viscosity calibration. What if I send that to one of the high viscosity fields that we have in this world area, or Venezuela, or Canada? A dramatic shift in performance. Absolutely huge shift in performance. As much as 1.5% in the worst case scenario. Again, why am I saying this? Is because, well, we're talking about calibrating meters, and once again, it's the details that matter. The details that are key to making sure that we can trade equitably, assure flow, operate safely. The third facility I'm going to talk about that's oil and gas related is our AMF, our Advanced Multi-Phase Facility. Truly impressive. Sharir was over a few months ago to visit, and I think he was genuinely impressed. I think it's fair to say it's industrial scale. 80,000 barrels per day, 350 million standard cubic feet per day to use oil and gas units. All with quite low uncertainty. It has industrial pressure and temperature ranges, 140 bar, 43 degrees. It doesn't capture everything, but it captures a large chunk of the conditions that people face when they're operating these meters. And huge variability over the gas volume fraction. We can have no gas or all gas, and huge variability over the water cut range. We can have all water or no water. So a really impressive, fantastic, facility. The key for me here is we're often criticised for not using natural gas and crude oil. We use Exol D140 for our oil. We use nitrogen for our gas, which is inert, and we use salt water, saline water, which we make by putting kitchen salt into tap water to get our salt water. Now why do we do that? Well, they're surrogate fluids, but they're surrogate fluids for a reason. If I use live fluids, and there are labs that do use live fluids, you see there that there's a lot of mixing. You know, some of the components in the natural gas go into the crude oil, they come back out. There's some of the components from the natural gas mixed with the water. And basically what that means is we might be able to measure accurately through our reference meters, but we cannot, to a low degree or to a low uncertainty, calibrate the meter under test because we don't know the properties of the fluid. So we've chosen to use inert gas, synthetic oil, and salt water precisely because we can understand the fluid properties better. We have a knowledge of density with synthetic fluids, which is 2 orders of magnitude greater than our knowledge of densities with live fluids, literally because the hydrocarbon gas and the crude oil can't make up their mind whether or not they want to be hydrocarbon gas or crude oil. So again, it may seem as if that's a cop-out, not using crude oil and natural gas, but it's a decision based on better metrology. Once again, the experience of my colleagues over the years has shown us that for good meter calibration, it's the details that matter. Finally, on this, before I talk about CCUS and hydrogen, natural gas and crude oil are extremely complex fluids. Natural gas has 15, 20 components. Crude oil, 150, 200 components at worst, especially heavy crude oil. And it's not too difficult to understand the fluid properties of any one of these components, but when you mix them all together and start changing the pressure and temperature, the fluid properties are extremely complex, which is why over the last 30 years we've developed a program called PPDS, which basically has over 1,500 compounds in the database. And that allows us to tell the fluid properties, like the density or the viscosity of a multi-component fluid at a specific pressure and temperature. That's important for metrology, it's important for flow assurance, and it's important for safety. And it allows us to draw the phase envelopes, and we'll see later on that again, that's critical. If I think I've got gas, if I want gas going through my pipe, I better make sure I do have gas going through my pipe. Same for liquid. So this software, the PPDS software, as I say, it's been developed over 30 years, 1,500 components, all empirically based, and it's proved invaluable in making sure that flow assurance in the oil and gas industry, as an example, can be done with a high degree of confidence. So, I think it's fair to say that we've learned a lot about metrology challenges over the last half century in the oil and gas industry. For example, the fluid property effects on flow meters we saw earlier, viscosity and pressure, and also multi-component PVT complexities. Back at East Kilbride, in my office, we're now equally focused, it is about 50-50, on the new challenges that come with metrology for net zero, in particular hydrogen and CCUS. And we know that once again, it will be the details that matter for fluid properties and metrology for hydrogen and CCUS. So, what are we doing about that? If we consider hydrogen, we've done a lot of good work here. I've done a lot of good work. We already have an operational mobile prover for hydrogen refueling stations. Turns out that if you're filling your car up with hydrogen, you weren't likely to get within plus or minus 10% of what you thought you were buying. Sometimes you were getting 10% more, at worst, sometimes 10% less. Why? Because it's a new industry, they're not metrologists, so it was quite clear that a solution had to be found. So what we did, in conjunction with others, is develop a mobile gravimetric proving rig which we can drive around the refueling stations and calibrate or validate the meters in situ. The compliance, for those of you who are interested, is OIML R139. We also have a small-scale research, test and calibration facility for hydrogen and hydrogen mixes. Now, it's fully operational, available for hire. It's got some pretty low uncertainties. We use hydrogen, methane and nitrogen. And again, we do that on purpose. We want to have fluids that we understand the properties of in order to make the metrology as good as possible. We use methane as a substitute for natural gas because natural gas is maybe 95% methane, so it's pretty close. But we understand the behaviour better. Now we have to consider industrial scale hydrogen metrology. Well, I'm going to come back to that. Okay, I've got more on that at the end of my presentation. And of course, for hydrogen, it won't be pure hydrogen. There will be some impurities, hopefully not too many, but there will be some. So we need to understand the thermophysical properties. And what we've done is we've built a thermophysical properties lab. And again, I'll come back to that later. There's good reason for me just skipping over it just now. Okay, now I can consider carbon capture. Carbon capture requires traceable metrology. It's a fiscal transaction. There is going to be money changing hands. There's going to be tax paid on carbon transport. And there's quite a few places where the metrology is required. You know, onshore transport, buffer storage, offshore transport, injection. Just like the oil and gas chain in reverse. Going back down to where it all started, it's quite, it's quite romantic really. The same molecule will end up where it came from 50 years after it came from there. But that requires traceable metrology. And also, CCUS, the carbon dioxide in CCUS is not carbon dioxide. It's maybe 90 or 95% carbon dioxide, and it's 5 or 10% of a wide variety of contaminants, which make it a very complex fluid, just like crude oil or natural gas. So we need to understand the properties of that fluid if we're going to be safe and efficient and trade equitably. So we think that this is the kind of range that CCUS will be operating in. There'll be the liquid phase, the dense phase, which is just liquid above the supercritical pressure, the supercritical phase, and the gas phase. We think that the industry is going to unfold, like this. Ship transport down here in the liquid phase, onshore pipelines in the gas phase, onshore pipelines, some of them will be dense liquid or dense liquid, and some will be supercritical, especially as we get towards the re-injection point. And there'll be multiple components in it. There'll be 20, 30 components in it. So this is quite complicated. There's going to be multiple phase changes during the transportation and storage process, and it's going to be phase changes with a complex fluid with a wide variety of contaminants. So this is just shaping up to be exactly the same as the oil and gas industry in many, many ways. They're doing everything they can to avoid two-phase or three-phase flows. Yep, let's see how that works out, but we're trying, we're all trying. The issue here is a lack of traceable facilities with a primary standard for CO2 measurement. And I'll be clear here that some of the things I'm about to describe are collaborations. This is not entirely TÜV-SÜD NEL. We are working with many NMIs, many academic institutions to work towards a solution. But I'm just describing TÜV-SÜD's part in that journey, if you like. So the way that it's been approached is a dual channel approach. There's one channel. Can we calibrate with an alternative fluid? Do we need to have CO2 labs? Or can we just use water or nitrogen or natural gas? But also, as metrologists, we kind of accept that we do need a primary standard based on CO2. And it's also clear that these approaches are interlinked. Okay, this is going to be a journey where we're slowly getting to the truth about CO2 measurement. We're involved with a project called NCASE, where, I'm just going to check my time here. Yep. This is concerned with liquid CO2, a project called NCASE, and basically it's asking the question, well, can we calibrate with alternate fluids? Okay, can we? What we've done in collaboration with many other organisations is build a transfer package. We're then going to calibrate all the meters, or we have done actually, I'm saying past tense, this is done, we calibrated them all in water. We applied the corrections from the water calibrations just to try to have some sort of baseline, some sort of reference to deal with. We then tested the same meters in our EPAT facility with the oil that I mentioned earlier, the elevated pressure and temperature. We then tested the meters in liquid and dense phase CO2, and then we assessed whether or not you can transfer water calibrations to CO2. Now, this research is ongoing. There's lots of information available. I have a QR code at the end, and it's fascinating. I mean, it's absolutely fascinating to see how it's unfolding. So here's the transfer package. The transfer package is a 2-inch orifice plate, 2 clamp-on ultrasonic meters, 2-inch, a 2-inch turbine meter, and a 1-inch Coriolis meter. It's about 5 meters long, so we can transport it on the back of a lorry. Here is the package being calibrated at our water facility. Here is the package being calibrated at our oil facility. And here is the package being calibrated or tested or checked at the Institute for Energy Technology in Norway. And this was supercritical and liquid CO2. Quite a neat little package. 4 technologies in one. Saves a lot of time at the calibration lab. And so here's the results. We have a plus or minus 2.5% band on these charts because the UK emissions trading scheme has settled on plus or minus 2.5% for trading. Okay, I have no idea how that will work out for the rest of the world or what will happen in the future, but that's what it is just now. And the results are extremely promising. 2 graphs here, both well within the plus or minus 2.5%. One thing which is of interest to me is you can see slightly more scatter on the graph on the right-hand side. Slightly interesting to me because I'm the kind of sad guy who finds these things interesting. Over here, we have measured the density. And over here, we have used an equation of state to calculate the density. I think we used the Gerg 2008 equation of state. And this large spread, or larger spread, we think is due to the equation of state having a larger uncertainty near the phase boundaries. And that just requires a bit more investigation. Because now we're focused on CO2. Previously we were focused on methane and butane and pentane, the oil and gas stuff. So we think, or my intelligent colleagues think, that the equation of state is maybe not quite as good as it could be. And that's worth more investigation. And that's great. I mean, that's great. The results are very promising. Oh, sorry, just quickly there, you can see the water calibration, the oil calibrations at NEL, 3 liquid CO2 calibrations, and 1 supercritical calibration, just to make it clear that we're talking here about different fluids, different phases. So really quite good results, very promising. However, they are a relative comparison. All of this data assumes that the orifice plate is correct. They're just a reference to the orifice plate. There is no primary standard. They are a relative comparison. A primary standard is still required. So we're working towards that. We have our high-pressure gas loop, which we have repurposed now. We can take out the nitrogen, put in CO2. And that's quite useful, we think, because the facility range coincides with a lot of the gas pipeline that we saw earlier in the presentation. So it's fantastic. It's a great facility, 0.35%, almost 10 times better than the 2.5% requirement for the ETS, but it's not a primary standard. It still uses reference meters which are calibrated elsewhere. In terms of the liquid and dense phase CO2, we're making great progress at NEL. We're building a primary standard based around a compact prover. We'll be able to bring meters in and using mass and time calibrate them. So we will have a primary standard. I was going to say 2025, but 2025 is actually pretty close now. Maybe mid-2025, not quite sure. And again, we think that will be useful because here the operating envelope has been chosen to overlap the dense phase pipeline and possibly some of the sequestration conditions that will occur during the final stages of pushing the carbon dioxide back underground. That is a primary standard. As I mentioned earlier, carbon dioxide for CCUS is not carbon dioxide. It's many, many components. So we're building a thermal-physical properties laboratory. We have built, it is operational, and it's designed to allow us to calculate density and speed of sound measurements for both CCUS streams and hydrogen streams. So the kind of typical components, obviously, are CO2 and hydrogen, but we can also introduce nitrogen, methane, argon, water, NOx, SOx, ammonia, all the things that we understand will be part of CCUS carbon dioxide. It will cover the gas, the liquid, and the supercritical phases. And as a result, and because of that, it has a large pressure range up to 1400 bar, and it goes from pretty chilly to pretty hot. And we think that will cover most of the needs of our customers and the industry. Now, I showed you earlier the gas primary standard. I just skipped over it in terms of hydrogen. But we're also building at NEL a gas primary standard. The main components will be nitrogen, hydrogen, methane, and CO2. That's initially, we can swap out these components. Obviously, we think the main interest will be CO2 and hydrogen for the CCUS and hydrogen industries. More are planned for the future. Basically, if it's safe to do so, we can fill this rig with multiple components of gas. So we can get like a calibration gas that you would get for a gas chromat with a particular set of contaminants and use that rig. So we're hopeful that that's going to be really useful for our customers. It is a primary standard. It operates on the PVTT principle, pressure, volume, temperature, and time. It's like a prover in reverse. We don't push the fluid out the tank or the cylinder. We bring the fluid into the tank. We know the pressure, we know the volume, we know when the tanks are full, we weigh them, we can then calculate a density and a time. So we have a kilograms, a volume, meters cubed, and a per second. So it's a primary standard, mass, length, and time. Again, I anticipate that being commissioned next year. And there's a lot of work involved with commissioning. I'm starting to realise you can't just say, right, that's it, it's done. You've got to get comparisons done and take in references from elsewhere. But that's the plan. Sometime in 2025. The mass flow uncertainty is our target is 0.2%, which is pretty low for a gas facility. The stretch target that my colleagues have given themselves is 0.15 or 0.1%. That's what we're really aiming for to make this a kind of world-class facility. I'm coming to the end, folks. You'll be glad to hear. In the presentation material for this course, there's a QR code. I would suggest that you go and visit the website tufsud.com.uk. There's a huge amount of information there, white papers, case studies. It really is quite an impressive library of information that's been built up over many, many decades. The webinars, I will warn you, some of them are me going on and on and on for an hour on various topics. But as I say, there's a lot of really useful information there. And so just to sum up, folks, TÜV have been providing traceable metrology for the oil and gas industry for over half a century. We have been a key part of developing technologies, standards, and practices, and I can't, that's no exaggeration. You know, ISO standards were developed there partially, government regulations, meter manufacturers have improved their meters at our facilities, learned more about them. We have academia in there doing research every few weeks. And what's become clear is that the skills and experience gained are directly transferable to the energy transition. Hydrogen and carbon dioxide are fluids. They have a viscosity, they have a Reynolds number. You know, all of the stuff that applied for oil and gas applies equally to CCUS and hydrogen. Hydrogen. We continue to be at the forefront of developments in traceable metrology as we move towards a net zero future. And we are pretty confident that for net zero metrology, details will also matter. So folks, thank you very much. Yep. Do you want to say something, or do I just ask for any questions? Yeah. Any easy questions? Marco, this will be a hard question.
About some relative things. Oh, I can use the mic.
Yep.
Relative things. And I said, you said a prover is the best solution, high cost of ownership, high cost of operations.
Yep.
We all know that. But in business, it's not about cost, it's about revenue. Could you elaborate on that? Because now you have stated, hey, it's too expensive, just forget about it. And I'm sure it's not your opinion.
No, do you know, I mean, it's just the fact that every measurement point undergoes a cost-benefit analysis. So, if you have 1 million barrels of oil a day, that's a crazy figure, it's like 50,000 barrels of oil per day, and it's a custody transfer measurement, you can justify buying a prover and maintaining a prover for that. Yep, absolutely. If it's an allocation measurement, well, that's, it's maybe harder to justify. If it's a process or control measurement, it's almost impossible to justify. So my point there, I suppose, Marco, is a very valid question, was that, there are clearly some measurement points where a compact prover pays for itself within days in some cases, There are other cases where it's harder to justify. You may want to rent a prover to come in. Even that, the additional hardware costs for takeoff points and bringing in the technicians is expensive. So yeah, it's a very fair point, Marco. Not every metering point has its own compact prover, and I think the reason for that is entirely financial. As I say, 100,000 barrels per day, you want a 0.25% uncertainty. Yeah, your regulators will demand that you have a prover either there or coming in regularly. If it's another less critical measurement, but you still want to have some validation of the uncertainty, then possibly coming to force or NEL is the better option. Is that a reasonable answer?
It is. Thanks.
Cool. Anyone else, folks? Oh, yep.
Yeah, hello, Ilya from OGS. Just wanted to ask you, we're talking about 2.5%, which is huge. So what's your expectations? What it come down at the end? What do you think industry will aiming to?
So this is now opinion. My opinion is it will come down. I don't have any close involvement with the higher levels of government. I do meet some of the regulators, just before it turns from engineering to politics, when it becomes crazy. I get the impression if they'd said, okay, it has to be plus or minus 0.5%, that would discourage people from developing the industry. So I think that they have gone for an uncertainty. This is just an opinion. They have gone for an uncertainty that they know or they guess is achievable in the short term. At least then people will say, okay, I'm willing to invest in this, I'm willing to develop the industry. And as time goes on, if it turns out we can get results like that all the time, then that may well be tightened up. I mean, it is a great question, because so I've done this for 30 years, right? Hard to believe, eh? And I've always, since the day I joined, it's been 0.25 or 0.3% for liquid and 1% for gas. And it hasn't changed in 30 years. But I am genuinely curious, if I had joined in, say, the 1940s or 50s rather than the 1980s or 90s, was it always 1% for gas and 0.25% for liquid? Was there a time when it was 2% for gas? I mean, there are some people here, that have been doing it for just as long as me. Very few have been doing it for longer than me now, unfortunately. But I don't know. I mean, I would genuinely like to know if anyone here used to sell or buy natural gas on plus or minus 2%, or sell and buy crude oil on plus or minus 1% or 0.5%. But back to your point, 2.5%, I mean, we nailed it on the first test. So I think that's going to encourage people to invest in developing CCUS. It will mean that metrology is not a stopping point. But if it turns out that it's a breeze, then I can see them bringing that down. Yeah.
Hi, Cole. So if we're going to get down less than 2.5%, surely the two components, and one will be the equation of state has to get better.
Yep.
Looking at the results that you had, I'm sure that the variability is down to the impurities.
Yep.
Probably a big contribution there.
Yeah. Yeah.
And also the, well, I suppose the equation of state for your volumetric calibration to mass as well. But we'll be looking at large meters for pressure drop purposes, I'm sure, because we'll be operating at very high pressure.
I mean, again, Stuart, great points. I mean, the phase change in the complexity is going to be a big deal. So if you start shoving everything into a 1-inch Coriolis meter, you're going to be inducing phase changes, and that's great news for the Coriolis manufacturers. They'll be selling all these massive big meters, I think Coriolis will prove extremely popular because it's a mass meter. I think the package there. Sorry, just to be clear as well, that I showed the Coriolis versus Orifice. The other data will be coming out shortly. My colleagues will be releasing all of that data. But yeah, I mean, the equations of state, again, I'm kind of speculating here, Stuart. The focus was on oil and gas. So methane, ethane, propane, and carbon dioxide was like a wee bit at the end, And it now appears that when you're talking about, 90% carbon dioxide, that perhaps there's just not enough empirical data to make the equations of state as good as they could be. And there's also the challenges that my colleagues tell me, where they think it's the phase boundary when you're getting close to that, and you always seem to be close to it, in CCUS, that there's maybe a bit more work done. But you're right, research into the fluid properties, I think, is going to be a key part of bringing these uncertainties down if need be. Yep.
And obviously the larger the meter, the bigger the effect on pressure has.
Yep.
You're probably going to have meter manufacturers at your door wanting to refine their pressure corrections, because we're going to be operating at 200 bar potentially.
Well, that's right. Again, and we're more than happy with meter manufacturers knocking on our door. But you're right. As they repurpose these meters for a new era of custody transfer and physical measurement, they'll have to do more research. I mean, we did it for oil and gas, as that hopefully explained. 50 years we've been doing this. We did it for orifice plates originally. ISO 5167. Now we're dealing with new fluids, and it's like people say mass is mass. Yeah, but physics is physics. There's always complexity there. Chemistry is chemistry. There's always a little bit of complexity, and I just think that research, collaborative research, will be the way that we understand these issues better. Oh no, Mark, it's going to be really hard.
Okay, sorry. I think it was a presentation in Birmingham a few months ago, and you've been talking about 2.5% uncertainty on measurement of quantity. In Birmingham, I thought they said the ETS was based upon pure carbon dioxide. So what are you going to do about that 5% of the other crap that's in there, and how are you going to deal with that? Because in my concept, carbon dioxide as a liquid is probably a low viscosity liquid, and some of those components are going to be essentially immiscible. So the sampling is going to take most of that 2.5% uncertainty straight away.
Yeah. Again, that's a great question. I just hope you don't expect an answer from me. But you're right. I mean, you're right. Just like, my understanding of, say, LNG is, we're talking about measurement and analysis, and the big elephant in the room is sampling, proportionate representative sampling. I really don't know, Mark. I mean, I really don't know. You clearly already know more. I'm not being too self-effacing here, but you clearly will know more about the challenges that if you have CO2 and amine and H2S and a bit of water and some carbon monoxide. I can see that you're already thinking this is going to be tough to sample. I mean, I've spoken to people at Emerson and they're saying I can analyse it, but you'll have to spend £1 million on like 15 analysers. One for this, one for that, one for that. But just like oil and gas, the sampling is absolutely essential and tends to be overlooked because people who are not metrologists say, well, but how hard can it be? You put a drinking straw in the pipe and the fluid goes to the analyzer and that's it. That's it. What's the problem here? Clearly someone with your knowledge is already looking at that and thinking, oh no, there's your 2.5% gone immediately. So I would imagine it'll be the influence of people like yourself who actually make sure that we don't lose track of the fact. I put up a graph there that shows less than 2.5% and we all go out and drink some champagne or, book a holiday and relax. The reality is that a 15-component CCUS mixture, just even what you're saying to me right now, Mark, that's going to be incredibly challenging to get a representative sample from the pipe into the analyzer. So, as I say, I think it's the influence of people like yourself and the others in this room, to just not ignore the fact, to just be cognizant, do some testing, do some research, but yeah, if you say it will take up most of the 2.5%, then maybe 2.5% was a bit tight to start off with, maybe we should start at 5, I don't know. But very good point, Mark. I don't have an answer other than research and testing.
Hi, my name is Ashwin from BAPCO. I just, since you were talking about that one software which you are using for various composition of gases, right?
Yes.
So when you are doing customer for a client meter calibration, when you are providing them the certificate, are you giving that correction figures along with that?
Well, we have the software for complex fluids, but the fluids in our lab are purposely not complex. So our gas facility is bottle purity CO2 or bottle purity nitrogen, 99.9%. Same with our multi-phase lab. Our water lab is water. So while we have the software PPDS to derive fluid properties for complex fluids, when we're calibrating a customer meter, we do not use complex fluids. We only use, and people, people sometimes criticize us for that. Why don't you use natural gas? Well, one, it blows up, and we're not near a big pipeline. There are people like Marco and Force who do use natural gas, hence the success of Force. We have gone down a different route because we're a National Measurement Institute, and there are definitely some disadvantages to that. But to answer your question, we don't use complex fluids in our labs.
Thank you.
My pleasure. Sorry.
You mentioned about virtual flow measurement. So you
Yes.
have some software to do that, or
Yes.
do we need any physical meters to have an accurate measurement on that?
That's right. Yeah, yeah. It's a verification tool primarily, but it's demonstrated that it can be used as a standalone meter. It's based around existing instrumentation. So every wellhead has a choke valve. As far as I know, every single wellhead in the world has a choke valve, which is effectively a restriction in the flow. It's like a variable orifice plate. And also every wellhead has upstream and downstream pressure and temperature. And then usually, and that's the core, that's the basic inputs you need for the virtual flow metering model to work. But it can be enhanced if, for example, you have a water cup meter or a densitometer somewhere nearby. Or usually there's a test separator which can be used for comparison purposes. What we can do is we can use either physics-based models or machine learning-based models or a hybrid of both, and we can take historical data from a wellhead. I mean, sometimes they have a multi-phase meter, and that's great. We can provide comparison. But we take that choke valve position, pressure and temperature, flow rates, separator data. We train our machine learning models on 8 or 9 months worth of data, 8 or 9 days if that's all you have. And then the machine learning model actually looks at the live data, choke valve position, pressure, temperature, and predicts an oil, gas and water flow rate. We have one just now in the Norwegian sector of the North Sea, and it's estimating the gas flow rates to within about 2% and the oil flow rates to within about 7% of their multi-phase meter and their separator. It's a fantastic assurance tool, but it can be used as a standalone virtual meter. And you know, one thing I would like to say is that we really are in a unique position. Having that industrial scale advanced multi-phase facility means we can actually go and test the models. You know, we actually, every day, if we need to, we have a huge industrial scale multi-phase facility. So we can move the choke valve, we can reduce the water, we can increase the oil, we can drop the pressure, we can increase the temperature. So the work that my colleagues have done has been astonishing. You know, some of these data scientists are angry that they're 1% out from the reference meters. And I'm thinking, you have no idea how a multi-phase meter performs in real life, you know. So yeah, basically choke valve acting as a variable area orifice plate. Pressure and temperature, machine learning models, separator data if you have it, water cup meter data if you have it. Physical models are sometimes used, hybrid machine learning, but yeah, we have a couple in operation just now and customers are very happy.
Thank you.
Anything else, folks? Okay, I'm done. Thank you very much.
An excellent overview there. Thank you so much from Tuvzud, and thank you to Colin Lightbody. A brilliant insight there. And any other further questions, please do make sure to speak to any of our speakers later in the day and, of course, in our upcoming breaks. And thank you for all the questions as well. As I mentioned, we really want to make this as interactive as possible, so please do get some really good questions going throughout the day. Now, ladies and gentlemen, our next speaker is going to be running, as I mentioned at the beginning of the event this morning, he's going to be running his session in the meeting room just in front of the ballroom, which is just besides the OGS booth. He's going to be taking a look at commissioning, optimizing and fine-tuning non-radioactive MPFMs for accurate, efficient and well monitoring across multiple sites, aligning with industry standards. So if you would like to join that, we can fit 12 people, around 12 people in there as well. So please do make sure to attend if you would like to. This is going to be led by